Good afternoon, everyone. And I'm Aditya Savio, as mentioned, and my home institution is at the Tartu Observatory in the University of Tartu at Estonia. And I'm also an external collaborator with the Motion and Teaming Lab with Dr. Ott as my advisor. Thank you for your presence on my talk towards the multi-agent exploration of small solar system bodies. But to begin with, small solar system bodies, including asteroids and comets, are generally considered to be dynamic targets, which means that they host very uncooperative environments in case we would like to explore them from close proximity. However, these are quite important elements of our universe that have great motivation to be studied. And this talk is motivated by the fact that to study such objects in space, it is essentially required that a multi-agent system working efficiently over optimal motion planning algorithms are able to explore these objects from vicinity and ensure that they yield a high scientific return. In our work, which was presented at the International Astronautical Congress between work done by myself and advised by Dr. Otte, we consider the problem of simultaneously planning and replanning the motion of a spacecraft in the gravitational field influence of such small solar system bodies, while we simultaneously map the gravitational influence as well. And the idea is that as we progress, the motion of the spacecraft becomes more stable based on the immediate understanding of the gravity field model. The motion planning spaces are defined in a way that we extend a target space where the spacecraft is restricted to explore the small body, and any space which is quite close, which may be dangerous for the spacecraft to crash into, is considered to be the danger space. Is considered to be the obstacle space, and any space outside the sphere of gravitational influence is considered to be the danger space. We used sampling-based motion planning with a receding horizon optimization to sample waypoints over sparsely exploring random trees, and in the gravitational influence of the body, we are able to generate a trajectory that follows an optimal or that generates an optimal solution, a near optimal solution to sort of orbit this body. In this simulation, we can see that as the explorations in orbit progress, the gravitational field information gets more and more well-defined, which helps us to concentrate the gravity field model to a higher fidelity. Simultaneously, as the gravity field model is made well known, the erratic motion of the spacecraft tends to get smoother, which implies that the recent understanding of the gravity model was considered in order to efficiently plan a more stable orbit, and in another sense, actually replan the in-orbit maneuvers based on the updated information of the gravity. The plots over here show that we moved from an undulated trajectory to a smoother trajectory, and simultaneously, the gravity map that we had as an initial estimate, which was quite a low fidelity, by the end of the simulations, we were able to generate a gravity potential map, which accommodated the smaller forces, which usually cannot be observed from remote sensing observations from the Earth for such small bodies. However, to observe such pristine bodies, it is potentially hypothesized that a large number of agents or a multi-agent system shall be able to study these bodies from multiple spatial locations, which may turn out to be strategic to, again, provide more information about certain bodies. And these would perform spatial mapping, hopefully with some onboard autonomy, that may be able to map bodies that we have not yet been able to study even through remote observations. For example, the recent witnessing of the Oumuamua planetary object that had a flyby through our solar system. In this work, which was also presented at the IAC Congress, we used the sparse RRTs to plan a flyby through certain bodies whose gravitational field extent is known. And in that sense, we are able to generate a particular trajectory over the sample waypoints. And using the hyperbolic equations, the solutions from the waypoint exploration can be used to generate hyperbolic trajectories which accommodate the gravitational curve of these bodies as well. For simplicity, in the mission scenario, we consider the small solar system body as the only moving object, and it is observed from various spatial locations by multiple agents. And this represents a high velocity flyby through the agents that are continuously observing. And we perform surface reconstruction for the particular flyby scenario, where single agents, frames from a single agent and frames from multiple agents were compared, and it is quite evident that more information was achieved, and hence with multiple agents, and hence a greater area of surface was being able to reconstruct, which may be useful also to study the surface activity for such small solar system bodies. Such an approach is not just feasible for such bodies, but also to investigate event outcomes. For example, in the mission scenario where we shall be impacting the surface of Didymoon, the simulation of the plume ejected from the surface can be strategically mapped if we are able to place these multiple agents in positions which are near optimal to be able to study the event closely, as well as the multi-agent topology that we have has been identified to have to be developed on strategic motion plans, as well as quite efficient task planning and allocation. For example, on the surface of Mars, we now have a system of heterogeneous robots, which perhaps could be used within this topology to study terrestrial activities such as dust storms and possible tornadoes, and all in the case of providing a high scientific return to be able to map and understand such dynamic events more closely. With this, I would like to thank you for your time and attention.
Any questions for Aditya? Yeah.
Yes. Right. Oh, sorry. How did you determine? We did have to validate this sort of fidelity by comparing our particular validation for this approach, trusting that the spacecraft used in order to be able to sort of
Which one do you want?
tackle the gravity that it may have not known earlier. So we saw that there was reduced thrusting as the exploration progressed, which meant that lesser thrusting was required to tackle the gravity, and hence we bias the low fidelity over the high fidelity. Fidelity is not on my. Yes, it is on the description of the thrusting values that was.
So thank you so much, Aditya, for a wonderful presentation.